Welcome and hello. This is a video exercise in HY-8, and in this exercise, we're going to be dealing with alternative designs. This is a feature that's built into HY-8 to help modelers design their culverts. All right, so let's go ahead and get started. I have the HY-8 interface up on the screen here, and the first thing I'm going to do to introduce this problem is to open up a PowerPoint with some requirements for the culvert. Here we have a design discharge of 2000 CFS. Minimum freeboard is 4 feet. And you can see in the diagram here, the roadway elevation is 70 feet. So 4 feet below that is this 66 feet. This is the highest that the water is allowed to rise up to. After that, the allowable culvert shape has to be a concrete box, so the material is concrete. And then the available span for each of the culvert barrels is 6 feet, 8 feet, and 10 feet. And then the acceptable span to rise ratio is either 1 or 2. So what that means is if the span is 6 feet for a 1-to-1 ratio, then that means the rise is 6 feet. If the span to rise ratio is 2, then that means the 6 feet wide would be a 3-foot high rise for that particular culvert. So ultimately, these two lines here dictate the 6 different sizes, 3 times 2, 6 different sizes of concrete box culvert barrels for the design. The total width allowable is 60 feet, so we're going to have to make a check on that. And then what you're seeing here is I tried to draw this to scale. It's basically what's supposed to be a 6-foot wide by 3-foot high culvert barrel to sort of show you the perspective in the approximate scale. Also, the upstream elevation is 51 feet. That's the invert or the thalweg. And then the downstream invert, the outlet invert of the culvert is 50 feet. All right, so let's go ahead and get started. There are a lot more data that we need to input that I couldn't fit on one single slide here. So if you want to follow along, let's go ahead and start with creating our crossing and culvert. And also, one more thing is to set the units to US customary. So if you haven't already done that, just go ahead and set it to US customary. Then let's go project, add new culvert crossing. We can also just go up to the culvert and click on new culvert crossing. I'm going to start by inputting some discharge data. So over here on the left is the crossing data. Instead of min, design, max, I'm going to switch this to user defined. Click on define, and I have a total of 10 different flows. Now we only have to check one design flow, which is that 2000 CFS, but just out of curiosity and to also get a range of flow rates. See 2000 right here, number 8. This is the one that we care most about, but I just wanted to see what the rating curve looked like, and it's nice to have a little variety. So I'm going to just copy those from Excel, highlight the fields here in HY-8, and then Control V to paste. Okay, so those are pasted in. I'll click OK. Those will be the allowable flow rates that I can check or select from the dropdown once we get to this alternative designs button, which is the focus of this exercise. Okay, so next down we have our tailwater data. I'm going to input the data that we know. It's going to be a rectangular channel. And then the bottom width, that is going to be 60 feet. The channel slope I have at 1%, so 0.01. Manning's end value is going to be 0.013, which is typical of concrete, or 0.012. And then the channel invert elevation is going to be 50, because this is what it said on the PowerPoint on that slide, as well as for the downstream elevation. Okay. If we want to look at the rating curve for the flow rates versus our channel geometry, click that view button. Here's the data, excuse me. The water surface increases from 50.07 up to 55.32. Here's the plot. You can see the curvature. There's our 10 points should be on that plot right there. Okay, click close and OK. Next up is the roadway data. So for the roadway profile shape, I'll just leave it at the constant elevation. First roadway station, I'm going to leave that at 0. Let's see, we know the crest elevation is 70 feet. That's this right here. Roadway crest length, that's the length of the roadway, kind of perpendicular to the culverts. We'll just go ahead and say 100, as long as it's long enough to span that, 60-foot wide area we have to work with to put our barrels in. There's 70 paved, let's leave that. And then for the top width, I'm going to put 60. Okay, so that's it for the crossing data. For the crossing data, I'm going to just call this design 1. The default name up here is crossing 1, but I like design 1 better. All right, now we're moving on to our culvert data. It's giving us this culvert 1 as sort of a default culvert to start with. Before we use the alternative designs button, I just wanted to run one basic simulation with this design. Design 2 will actually involve the alternative designs feature. And I'm telling you that now because I'm going to name this culvert something simple, 6 foot, 1 barrel, which means I'm going to set the material to, let's see, the shape is going to be concrete box, the material is concrete. The span right here, this is that 6 feet that I was referring to. And then for the rise, if the span to rise ratio is 1, we'd put 6. If the span to rise ratio was 2, then we would put 3. So let's just leave it at 3 for now. Embedment depth will be 0. Manning's end will be 0.012, and then straight, and then the inlet configuration and inlet depression look good. Let's just use those values. Okay, we're almost done here. The site data, we're going to use the culvert invert data. That's good. For inlet station, I'm going to say 0. The inlet elevation will be 51. The outlet elevation will be 50. And then the outlet station, I will say, is 100. Actually, I'm going to say the top width is also 100 over here. I meant to hit 100. So this is all concrete. These are vertical walls, hence the rectangular channel. And yeah, I think we're good to go there. I'm going to leave this at 1 barrel only, and we're going to see perhaps some overtopping of the roadway. That's fine, because once we use the alternative design in our design 2, we're going to see how the number of barrels changes and how that calculation takes place. But for now, let's just go ahead and save first, or I guess I have to, let me click OK, and then let me save this. So I'll go up to File, Save, and now you want to navigate to where on your computer you want to save this HY-8 file. So that is right here, and I'll just call it exercise 4. All right, let's go back and run the analysis. So culvert crossing data, I could have just clicked on Analyze Crossing directly. Boom, here are our results. So with the flow rates ranging from 10 CFS up to 10,000 CFS, with that one culvert barrel that's 6 feet wide by 3 feet tall, here are the headwater elevations. They range from 51.75 up to 80. So that's 10 feet over the roadway. In fact, we're going to get overtopping as low as 352 CFS. So that's why at 200 CFS, there's no roadway discharge, but at 500 CFS, which is above 352, we do have roadway discharge, and that just continues on upward. So what that means is for our design flow rate right here at 2000 CFS, we know when using the 6 foot wide by 3 foot tall culvert box, we're going to have more than one single barrel because the maximum headwater elevation is not 73, but rather 66. The roadway is at an elevation of 70, but the freeboard is 4 feet, which means the maximum water surface elevation is 66. And that's a setting we're going to make as we transition into our design 2 and use the alternative designs feature. Okay, I just wanted to show this right here. If we click on the crossing rating curve right here, you can see that the overtopping occurs right here at an elevation of 70. That's why the plot changes in its shape right at about elevation of 70. Yeah. Okay. I'm going to go ahead and click close. The good news is we don't have to input all that data again. I'm going to take the design to 1, go right click, duplicate, and then this will be our design 2. So I'm just going to rename this from design 1 copy to design 2. I'm going to name this culvert. How about we rename it span to rise ratio 1. Okay. Now let's go ahead and edit that data. What that means is I'm first going to test the span to rise ratio 1, which is the square shaped rectangular box. We don't need to make any changes over here on the left side for the crossing data. But what we will do is modify some of this data. Now, some of this will automatically get changed in the alternative design. So looking through it, there's actually nothing I need to do. I could change this to a 6, but yeah, that's going to be taken care of. I'll click on the alternative design button, and now here comes a dialog box with data for us to fill out. On the left side, this is where we specify the shape, the materials, and the inlet configuration. So right now we have the concrete box selected for the shape, concrete is the material, and then square edge 90 degrees head wall is the inlet configuration. To keep things simple, I'm just going to leave it at that. So we're already fixing the shape, material, and inlet configuration. We're going to have enough to think about as it is with the number of barrels and then the shapes of those barrels. Okay, so leave that there. On the right half of this dialog box, we start with the culvert design options. We're going to set this first value to 1 because that is the span to rise ratio we're interested in testing. The rise increment, when applicable, is going to be 1 foot, which means we're going to start at, I guess, just 1 foot. And then with each iteration, it will advance 1 foot in the rise to check whether or not the other criteria are met. The maximum number of barrels, I'm going to set this to 8. Yeah, that'll work. Now, this is something I may have to check because if we're dealing with a 10 foot by 10 foot size barrel, we can't have 8 barrels since the total width is 60 feet. That would be 80 feet. And that's also neglecting the width of the sidewall of the culvert barrel itself, which we could probably assume is 6" to a foot. So anyway, I'm going to set it to 8 for now. I may have to increase it for the smaller sized culvert shapes, but let's just start with 8 and see what happens. And then the minimum cover is 2. I don't think that's going to be a binding constraint though, because I'm going to set the headwater down here. All right, so further down we have design requirements. Select the discharge. This is the list of discharges that we added earlier. And our design discharge is this one here, 2000 CFS. The design criteria, we want to leave it right here, lower than a freeboard. The other option is an actual water surface elevation. So we're going to set this value to 4 because we already gave the crest elevation of 70. That way it knows when running the calculations that there needs to be enough conveyance through the culvert so that the water surface elevation is at most 66, which is 70 minus 4. All right, as for these options down here, the maximum HW over D and minimum and so on, I'm going to just leave those unchecked. And then finally, the last step is to click this button at the bottom to determine design alternatives. So after clicking that, it's running through the different options for the different barrels one at a time. At the very top, what we see is the 1 barrel option, 1 barrel, 1 barrel. It's first going to try 1 by 1 box, a 2 by 2 box, a 3 by 3 box, a 4 by 4 box, and with each of these iterations, the calculated headwater elevation is exceeding 66 feet. We could check that ourselves if we want, but that's what's happening. Anyway, if I scroll down, it looks like the smallest square-shaped culvert that is just one single barrel is 14 feet by 14 feet. Now, that's not acceptable to us. So let's scroll down to the 2 barrel option, which is right here, 2 barrel, 2 barrel, 2 barrel. Again, because the span to rise ratio is 1, we're seeing the exact same span and rise value. There's 1 to 1, 2 by 2, 3 by 3. If I scroll down to the bottom, it looks like 9 by 9 is the largest that works. However, we were limiting our span to 6, 8, and 10 feet. So we're going to go with this for our 10-foot solution. It may not be optimal, but we'll have to do a secondary check because the results that we're going to be seeing will be 9 by 9. I'll show you what that means a little bit later. Let's just scroll down and check out the other 2 results that we're interested in. All right, so for 3 barrels, 7 by 7 is the smallest dimensions for a span by rise box culvert dimensions that would work. So we're going to have to increase that to 8 because 7 is not an option for us. And then finally, the 4 barrel solution is 6 by 6, which is an option for us. So we've got our 6, 8, and 10 covered. If I click close, we'll now see a table which may make a little bit more sense than what we were just looking at. I'm going to resize some of these columns here. All right, so what we're looking at here is the number of barrels from 1 up to 8, since we said 8 barrels in that interface. Here's the 14 by 14 solution for 1 barrel, the 9 by 9 solution for 2 barrels. So we're going to be taking these 3 solutions right here. This will be our 6 by 6, 8 by 8, and 9 by 9 for the 2 barrel, 3 barrel, and 4 barrel solution. Now we can actually use the headwater elevation calculated here for 6 by 6 because those are the actual dimensions that we're going to be using, 63.42. So I'll go ahead and write that down in my notes over here. However, I need to still figure out what is the headwater elevation for 2 barrels at 10 by 10 and then 3 barrels at 8 by 8 because these numbers here are using 9 by 9 and 7 by 7. Now we know that the headwater elevation is probably going to be a little bit lower and hence not optimal, but let's go ahead and knock that out right now. We'll go ahead and click close. And then what did I say? 10 by 10, and that's going to be 2 barrels. So I'll click 2 barrels right there, and then analyze crossing. I'm interested in this flow right here, 2000 CFS, and then the headwater is going to be 62.61. 62.61. Okay, got that in my notes. And then the last one is going to be 8 by 8 with 3 barrels. So back to the edit input data. Here's the span of 8 by 8. And then down here at barrels, I'm going to click 3. Okay. And then analyze crossing. All right. Here's our design flow rate of 2000 CFS, 61.53. So that's all recorded. What I'm doing here is demonstrating that the alternative design feature may not do exactly what you want it to do, but it's still a good tool to help you narrow down your options, especially when you think about all the potential hundreds of different options there are. It's just a tool. It may not get you the exact number you want. As for us, we had to do one more calculation there at the end for 2 of those sizes. Okay, so let's go back to our main page here. I'm going to create one more design, but instead of a span to rise ratio of 1, I'll make it 2. So let's go with a duplicate and then a rename. Okay. Now let's go with a rename here, change that to a 2. And then let's go ahead and open Culvert data and then alternative designs. Now, instead of a 1 here, I'm going to make this a 2. Everything on the left half of this dialog box is the same. We're still going to use a concrete box and use this square edge configuration. The rise, we'll leave that at 1. The max number of barrels is 8, and then the minimum cover is 2. I didn't check the width last time, but yeah, everything looks good. The width will be more critical with the span to rise ratio equal to 2 anyway. Everything else down here is the same. We're going to maintain that same minimum freeboard of 4 feet. So the max water surface elevation will be 66.0. And we're ready to calculate. So click the button at the bottom, determine design alternatives. Let that run. Okay. Similar as before, we have the 1 barrel solution, we have the 2 barrel solution, 3 barrels. I'm just going to go ahead and click close and look at that results table directly and resize this right here. Now the 3 barrel solution right here, that is our 10 by 5. So that's cool. We don't have to make any additional calculations. And 62.04. Further down, we have the 4 barrel solution and the 5 barrel solution and the 6 barrel solution all are using 8 by 4. Now, the one that we want to select would be the solution with the fewest numbers of barrels. That would be the most cost-effective solution. It would result in a higher water surface elevation because 3, 4, and 5 are resulting in a water surface elevation of 64.1, 60.4, and 58.47. However, what we're interested in as a cost-saving device and constructability is the highest water surface elevation that does not exceed or our violation of 66, which is going to be this right here, 8 feet by 4 feet. There's 4 of them. Okay, the last one is our 7 barrel solution and 8 barrel solution are both using 6 by 3. So by the same thinking of 8 by 4, we're going to take the solution that uses the least number of barrels. That's 6 by 3, that's 7 of them, for a headwater elevation of 64.00. All right, so those numbers are all below 66. That's good to see. As for doing the width check, remember we have 60 feet total width. That's another reason to use the fewest numbers of barrels. We're more likely going to satisfy that constraint. So 3 times 10 is 30 feet. That's certainly less than 60. And then next was 4 times 8, that's 32. That's certainly less than 60. And finally, 7 times 6 is 42. More than the others, but definitely less than 60. Even when you consider the side of each culvert barrel is, like I said, 6 feet or 6 inches to a foot, you're still going to have enough room with our widest alternative right here. Okay, so just a good check to make. Otherwise, we may have to have a second layer of some of these culvert barrels, but we're good there. All right, so to summarize things, we go ahead and close that up and then bring up the PowerPoint. Here is our results for the span to rise ratio of 1, where the 6 by 6 box required 4 different barrels, 8 by 8 size box, 3 barrels, and 10 by 10 box, 2 barrels. You can see in the gray coloring, that's where I've labeled the headwater elevation. So between these 3, 6 by 6 has the highest headwater elevation and presumably the best alternative if you look at costs and so on, but that's probably a little bit more complicated than just looking at the headwater elevation. So It's good to have multiple alternatives. And then for the span to rise 2-to-1 ratio, here are the three solutions. With a 6 by 3 foot culvert barrels, we needed 1, 2, 3, 4, 5, 6, 7. You can see we still have sufficient room for probably two more boxes or two more barrels. That resulted in a water surface elevation of, oops, hold on, I got 60, this one's 64.00. And then, yeah, the other two numbers are correct, 64.14 and 62.04. So 8 by 4, 4 of them, 10 by 5, 3 of them. And then here are the water surface elevations. So the highest water surface elevation when doing this analysis was the 4 barrels at 8 by 4, resulting in a water surface elevation of 64.14. Okay, going back to the previous slide, I had my numbers mixed up. The 6 by 6, that actually was a 63.42. So sorry about that. Those are the results that I have. And that is it for this exercise. What we did was we looked at the alternative design feature that's built into HY-8 by clicking on alternative designs, specifying the shape alternative, culvert design options, design requirements, running the computation, and letting the calculator help us design our culverts.